areas and arc length in polar coordinates. In rectangular coordinate xy system, we find the area under the curve f above the x-axis or between the two curves. In polar coordinate, we're finding the area bounded by a curve between two rays, alpha and beta, both measures from the positive horizontal axis. Thus, we're looking for this shaded area. The equation of the curve in polar coordinate is written as r equals f of theta. We have no formula to find the area of this sector, so with anything in calculus, we will divide this interval alpha to beta into n narrow sectors. Each of the narrow sector has an angle of delta theta. The area of the entire circle is pi r squared. Each sector has an area of 1/2 r squared delta theta. This can be seen by proportion. The sector has an angle of measure delta theta out of the entire 2 pi. It has an area proportional to the area of the entire circle. Simplifying this, we would have 1/2 r squared delta theta. If the sector is small enough, each of the sector is approximately the sector of a circle. The total area of the region bounded by f of x from alpha to beta is therefore the sum of all of these areas, 1/2 r squared del theta at I go from 1 to n, since we have n sectors. Note that this r depends on the specific interval, so it is Ri. But r is expressed in terms of f theta, so the area is the sum as I go from 1 to n of 1/2 f of theta I squared delta theta. And as n go to infinity, this Riemann sum would give us the exact area. The area of the region is 1/2 the integral of f of theta, the quantity squared d theta. We add up all of these sectors from alpha to beta. The lower limit of integration is therefore alpha, and the upper limit of integration is beta. This formula can simplify a lot of problems for us. For example, when we found the area inside the circle of radius a, for rectangular coordinate system, we have to use trig substitution to find the exact area, although we know that the area is simply pi a squared. The radius is a. In polar coordinate, the equation of the circle is simply r equals a. Thus, to find the area of this circle, we set up the integral as 1/2. We want the angle from 0 to 2 pi to sweep through the entire circle. The lower limit of integration is 0 and the upper is 2 pi. F of theta is simply a, and we squared it. This integral can be evaluated easily because a squared is a constant. The answer is pi a squared.